Okay, let's get started. Hello, everybody. We are very happy to have Professor Omid Amini from École Polytechnique Paris. He'll start his mini course today, and it'll be on the geometry of tropical varieties, as we see. So it'll lead up to some very recent, very interesting work in Hodge theory in tropical geometry. And so it'll be the same time today till Thursday. So we are very happy to have Professor Amini again. And Professor Amini, can you get started? If you're ready and get started, we're looking forward to it.
Yes, thank you very much for the invitation. I'm sorry that I cannot be there. Because of the pandemic, it's difficult to travel and so on. But I'm happy to be among you and giving this series of lectures. As Madhusudan said, the aim of this series of lectures is to give an introduction first to tropical geometry, which will be the subject of the 2 weeks starting from today. There will be a lot of talks which will be related to what I'm going to present. So the motivation of maybe the leitmotif of the development of tropical geometry, the current trend is to study families of algebraic varieties. Specifically, people are interested in answering questions where families of algebraic varieties degenerate to some algebraic varieties which are not smooth. So typically, the basic example maybe to have in mind is if you have a moduli space of objects. These objects are algebraic varieties of a given type. For example, in the case of curves, you have a moduli space of curves of given genus. And these moduli spaces are not compact. So in some cases, especially in the case of curves, and also in more recent work in the case of higher dimensional algebraic varieties, there are some compactifications you can define. And the idea is that there are several questions which motivate which concern the geometry of algebraic varieties when some of the corresponding points in the moduli spaces converge to a point on the boundary of typical compactification. So more generally, you would like to say things on families of smooth algebraic varieties which are defined over some base. And this base is not compact. So if you are working on a one-dimensional case, then typically there are general theorems which tell you that you can extend the family over some compactification of the one-dimensional base, given by adding some points. And the fibers which are put in there are not always smooth, but you can manage in characteristic 0, for example, to have semi-stable algebraic varieties. And in order to those are algebraic varieties which have a mildest singularity, and so basically tropical geometry comes and enrich. Provide somehow a smoother, by mixing polyhedral geometry and algebraic geometry, allows you to get more information about the fiber. So somehow it could be regarded as some way of smoothing by remembering some of the missing data when you have appearance of singularities. So this is in dimension 1, and then you can so in dimension 1. So basically, the things I'm going to tell you concerns the case of base dimension 1. So you have families of algebraic varieties which depend on one parameter, but you can also ask for the extension of everything that I'm going to present to the case where you are typically having families of algebraic varieties which depend on multi-parameter. And this is still at the very, very, very beginning of its development. It concerns the geometry of higher rank valuations and so on. So it's very exciting topic, and so everything which shows up, you could wonder if it's possible to extend it, including I think many of the other talks that people will present during these 2 weeks. So from the point of view of what I'm going to cover, so typically, so you can also ask about the analytic behavior of complex manifolds under degenerations. So this concerns like all the analytic invariants you can associate to complex manifolds, and you would like to see what happens when the complex manifold degenerate. So you have family and degenerate to something which is singular. And this is again, this requires developing analytic tools in the study of tropical varieties. And of course, this is the thematic of these 2 weeks. There are a lot of connections and applications to combinatorics. And in this series of lectures, I will give some applications of the materials which are going to be presented into combinatorics, purely combinatorial questions. So as it's already clear from this description, tropical geometry has a lot of connections to many different branches of mathematics, and I think this is still at the beginning of these interactions. So there are a lot of other applications of tropical geometry which will follow in the upcoming years. So as far as the plan of the course, my course is concerned, so the first 2 lectures are purely introductory lectures on tropical geometry. The aim is to give really the basics of tropical geometry. I give an introduction. Please stop me if there is something which is unclear. These 2 lectures are complemented also by some notes, handwritten notes of a course I taught on this also for another mini course, but this is more expanded. I will send it these notes, handwritten notes, to the organizers so that you can see some of the proofs of the theorems I will present during the first 2 lectures. And then the last 2 lectures are more advanced topics. It concerns the geometry of tropical fans, which are building blocks for more general tropical varieties. And then, so it's a local considerations of tropical varieties. And the last lecture is about the geometry, the global geometry of tropical varieties. And so these 2 lectures are mainly motivated by Hodge theory. And there will be some applications I will present of this, the connection to Hodge theory also during the last 2 lectures. Okay, so then let me start. If there is a question, I will be happy to answer. Otherwise, I start with the first lecture. So. Okay, so the main mathematical notion which is underlying the tropical geometry is the definition of evaluation. So evaluation here is defined over a field K. So K, this big field K, in these lectures always denote some field which is endowed with evaluation. So evaluation on a field K is the data of an application from K to R union infinity, which verifies the basic properties of evaluations. That V of A is infinity if and only if A is 0. So this is the only case where the evaluation takes value infinity. And then you have the property 2, which tells you that the valuation of a product is the sum of the corresponding valuations of the elements A and B, and the valuation of a sum is at least the minimum of the valuation of each of the summons. So typical examples, I think in elementary number theory, you have the field of rational numbers. You take a prime, and if you look at the p-adic so you look at the exponent of p, which appears in your rational number. This is called the p-adic valuation of that number. More in the direction of studying families of complex algebraic varieties, if you have the K, the field K, which is the field of rational functions. So these are in one variable. So these are all the functions of the form P T over QT, where P and Q are polynomials in T and Q is different from 0. So if you have a rational function of this form, then you just separate the power of t. You write it as t power k times some polynomial divided by another polynomial, and you suppose that these two polynomials are t-free, in the sense that p of 0 and q of 0 are different from 0. So it's easy to verify that this is the t-adic valuation. This defines a valuation which is called the t-adic valuation of this field C parenthesis t. So you have a more local version of this, which is the field of Laurent series. So C double parenthesis t. So this is the as I said, it is defined by Laurent series. So these are formal series of the form the sum ck t power k. So k is going through integer integer numbers which are bounded from below, and ck's are complex numbers. In this situation, you have to any formal series like this, you associate its t-adic valuation again, which is defined to be the minimum k, such that ck is different from 0. Yes, there is a question, please. I think there is a question by one of the participants, an online participant.
Somdatta, can you please ask your question? Okay, looks like some issue with.
Okay, so maybe I continue. So please,
Yeah.
Okay, so the algebraic closure of the field K, the field of Laurent series, is the field of Puiseux series, and these are all the formal series in t power 1 over n for some given n. So these are Laurent series in some rational power of t. So it's a union of C double parenthesis t power 1 over n. So this is this comes again with the valuation, t-adic valuation, which is again defined as the minimum k, such that ck is different from 0 if the element is written as formal Laurent series in t power 1 over n. So it's defined as t power k over n. So the valuation is k over n. Okay, so maybe a quick okay, so maybe a different formulation of the valuation. So this is also an opportunity to define the semi-field of tropical numbers. Tropical numbers as a set are the real numbers where you have added the element infinity, and on this set, you can define two operations, the operation of tropical addition and the operation of tropical multiplication. Tropical addition of two numbers is the minimum of the two numbers, and the tropical multiplication is the sum. If you define these two operations, you can see that infinity is the neutral element for tropical addition, as a plus infinity is the minimum of a, and infinity is equal to a. And 0 is the neutral element for tropical multiplication, as a times tropically multiplied by 0 is a plus 0, so it's equal to a. And it is easy to see that you have an inverse always for tropical multiplication, but tropical addition does not doesn't necessarily have an inverse for elements. So that's why it is called a semi-field. And if you, the advantage of maybe sometimes to have something maybe more conceptual in the direction of having developing algebraic geometry over in tropical geometry is to view valuations as morphisms of semi-fields. So K, it's a field that you can view it as a semi-field, and the valuation you can view it as a map from K to T, which verifies the property that multiplication is respected. And the valuation, the map at 0 takes the neutral element for addition of t, which is infinity, and the map on 1, which is the neutral element for multiplication of k, is also the neutral element for multiplication of t. And so this is the maybe the part which is different from the morphisms of fields, is that here you have you assume that v of a plus b plus va plus vb is equal to va plus vb. Actually, the right concept of morphisms in fields is to ask that va plus b, VA and VB, one of the three. Actually, yeah, so this is the minimum of VA plus B, VA, VB, and the right concept here is to ask that at least two of the minimum is achieved at least twice between the three elements V of A plus B, VA, and V plus BB. Okay, I will come back to this a little bit later. So the setup in what follows will be the following. I will have a K, which is a small k, which is a base field. And there will be this big K. Big K is always a valued field containing K, and we typically assume that K is algebraically closed. Okay. So the advantage here is that we can treat the case of somehow which is called trivially valued case and the non-trivially valued case together. So in the sense that K equal to K is a load. So when you are working with polynomials which have a coefficient in K, if K is equal to K, so typically the coefficients can have valuations, non-trivial valuations. But also you can have a situation, another situation, different situation where the valuation of K, when you restrict it to a small K, the valuation is trivial. Okay, so this will show up. For example, if K is equal to the field of complex number and you're working with C double parenthesis T, or the field of Puiseux series, then the valuation, the T-adic valuation over the complex numbers, which is the base field, is trivial. So typically, in whatever it follows, K is equal to C, and big K is the field of Puiseux series. But as I said, it can happen that K is equal to the field of Puiseux series. The small K is the field of Puiseux series. So this is typically in the situation where you have families of algebraic varieties, which are defined over, for example, over a curve. I think there is a question. Is there a question? No. Okay.
Yeah.
Sorry.
There is something in the chat. There is something in the chat, Omid. Maybe it's a comment. Nothing in the chat? Oh, okay. No, we are just handling that issue with unmuting.
Okay.
So you can go.
Okay, so let me then continue. Okay.
Yeah.
Okay, so in order to define the first examples of tropical varieties, these are the tropical varieties which come from algebraic geometry. So basically, you start with some algebraic variety and you put some coordinates. The two basic cases are the affine case and very affine case. So let me just say few words on what this means. So and then there will be some notations which are introduced, and I'm going to use these notations later on. So n is a natural number, and ank this is the affine space of dimension n over the base field k. It has coordinate ring, the ring of polynomials in n variables. Okay, so x inside ank is an affine variety, which has been given some coordinates because you have embedded this inside ank. This is a Zariski closed subset, and it has an ideal of definition I, which is inside the ring of polynomials in n variables, and it has coordinate ring given by kx1 xn. So typically, you can view x as the set of all points. So you have this x, so you can view I as the set of all polynomials which are vanishing over all points of x. So with respect to what is going to show up, the very affine case is typically more interesting. So this is the case where you, instead of looking at algebraic varieties which are embedded inside the affine space, you look at embeddings inside a torus, an algebraic torus. What is an algebraic torus of dimension n? This is denoted by Tnk. So this is the algebraic torus of dimension over the base field k. This is the open subset of the affine space which consists of all the points which have non-zero coordinates. So the coordinate ring of T and K is the ring of Laurent polynomials in n variables. So it means that you allow to have powers of x1, xn, which take negative values. Okay, so this T and K itself is an affine variety which can be embedded in an affine space of dimension 2n. Typically, you introduce a variable yj for the inverse of xi, and you put the equations xi times yi equal to 1. So T and K is you can put the coordinates and view T and K inside some bigger affine space, but for the purpose of defining tropicalization, you really work with T and K as a bit coordinate with its ring of coordinates, which is the ring of Laurent polynomials.
Sorry, I have a question.
Yes.
So this a variety is usually the solution to a set of polynomial equations, right?
Yes.
So in this case, I would assume the coordinate ring K is a set of polynomials for which, if they are set to 0, they would give rise to the variety. Is that the concept?
Could you repeat the last?
The coordinate ring. The coordinate ring. I assume the K of xi1 up to xin are a set of polynomials, right? As you just said.
Yeah, these are kx1, xn are the set of polynomials. I is the set of is the ideal of definition of x. So usually you assume that x is reduced. So this is really the set of all polynomials which are vanishing over x.
Yeah. So if you set the polynomials to 0, essentially the solution to the set of
polynomials is x. Exactly. Is the points of x. Exactly. Okay. I mean, I will talk about points of algebraic varieties, and this will be maybe more clear. So in the very affine case, you work with the Zariski closed subsets of this algebraic torus T and K. So these Zariski closed subset have an ideal of definition, which has an ideal inside the ring of Laurent polynomials, and the coordinate ring is given again by the quotient of. Okay. And of course, so more generally, you would like to define to glue these. So somehow, I mean, the more general situation is the case where you look at toric varieties, which are obtained by gluings of algebraic tori of different various dimensions. Everything. So that case also will be important, but I will postpone the treatment of this situation a little bit later.
And what exactly is an ideal? Could you please explain?
So an ideal is a subset of. So if you have a ring, you can define an ideal inside that ring, which is a subset, which is okay. So this is the usual terminology in basic algebra. So it is a subset which is closed under addition. So it's a good subgroup for addition, and it is closed by multiplication by elements of the ring. Like for example, if you work with the ring, the polynomial ring in one variable k bracket x, then the ideals are basically given by you fix a polynomial f, and you look at or you take all the multiples of this polynomial f. This is an ideal inside k bracket x. In general, so if you have a polynomial ring in n variables, like kx1, xn here, then the ideal I is finitely generated. So it is given by some polynomials f1 to fm, in the sense that I is equal to all the linear combination f1 g1 plus f2 g2 plus dots plus fm gm for gm are the polynomials inside here. So this is typically
And what does it mean by quotienting with respect to I? What does that do to the?
This defines another ring.
Sorry.
I mean, this coordinate ring. You basically you can. What I'm saying is that this is the coordinate ring here, but it has it is a ring which is also some set of generators, which are this x1, xn. And typically, as we will see, so this generating set is what is crucial in order to define the concept of tropicalization, to go from algebra to polyhedral geometry. Okay, so this is this you can view it. This is a ring which comes with a generating set, and you fix a generating set. You call them x1, xn. So this is a ring, and it has a generating set x1, xn. I mean, it's a read, so yeah, it's an integral domain. So
yeah, I think we can go ahead. Yeah.
Yeah. So for okay, so now maybe just to make more precise the concept of points. So if you have a field extension big K which contains a small k, then a k point of the affine space is a point x which has coordinates x1, xn. And these x1, xn are inside the big field K. Okay, so these are all the points of A and K with values inside K. So they are called K point, big K point. An of K is the set of K endpoints. This is the notation, and it is just a K over N. So now if you have a subvariety X of A and K, which has an ideal of definition, then the K point, a K point of X is a point X which has coordinates x1, xn, and x1, xn are inside K, and you have f of x is equal to 0 for all f inside I, the ideal of definition. Similarly, you can define K points of the torus, the algebraic torus T and K, and also sub-varieties of T and K, which are called the very affine sub-varieties. So these are so the K points of T and K are all the points x equal to x1, xn, such that all the xj's are different from 0. So these are basically K star over N. And the K points of a subvariety of T and K are all the points x1, xn, such that for all polynomial f in the ideal of definition of x, I, f of x is equal to 0. Okay, so here it's really the evaluation. So you get a number inside K. When you evaluate, you ask this to be 0. And this defines this. If this happens for all the elements f, all the polynomials f in the ideal of definition of x, you call it an x point and k point, a k point. Okay, so tropicalization. What is the tropicalization? Tropicalization is a way of just remembering. You look at all the points of a system of polynomial equations, and then you just remember the valuations of these points. Okay, again, so you have the setup is the following. This is just as I said, it's the base field. You have a big K, which is a valued field. So it is a field which comes with a valuation, which contains K, and you suppose that K is algebraically closed. So now you look at a K point of T and K. So these are, it has coordinates x1 to xn, and these xi's are elements of K star, big K star. Then the tropicalization of X is defined to be the point in Rn, which consists of the valuations of the coordinates. So it's v of xn up to v of xn. So this allows you to simplify the points which had coordinates inside big K by just remembering the exponents. If you're working, for example, with K C parenthesis T or the field of preset, you just remember the smallest exponent of T in the solution into your system of polynomial equations. This is a point of Rn. Okay. So now if you want to since we define tropicalization of points, we can define tropicalization of subvarieties. You define it as follows. You just take, as I said, you're looking just for simplifying the points of X, the K points of X, by remembering just the valuations of coordinates. So you set up the set trop of X, small x, for X, a point of a K point of the subvariety X. Okay. So this gives you a set of points in R power n. It is not closed. Generally, it is not closed. For example, if you're working with the field of preserved series, all the coordinates you see of the tropicalization of a point are rational numbers. So the set trop x for x a point or k point of x has coordinates will be inside cube over n. But then you take the topological closure of this set, and you get a closed subset of Rn, and you call this tropicalization of X. So for now, this is just a set. For us, this is just a set now, okay? And then we will see that this set actually has a lot of nice properties. I will give several examples today. I don't give the general structure of these sets today, but we will see that later. We will see that basically these simplifications still allows you to develop a lot of tools coming from geometry, like algebraic geometry or complex geometry. So, okay, so I give several examples now. Okay, so to make this more clear. Imagine that you are working in dimension 1, so n is equal to 1. It means that the torus, algebraic torus you're working with has dimension 1. So it means that the polynomials you're considering are in one variable. So they depend only on one variable, and this variable is called x1. So f, you take a f, which is a Laurent polynomial in variable x1. For example, here I took x1 squared minus a times x1 plus b. And we look at the k points for big K. So this is the big K. What are the K points of these this polynomial? These are, so K, this big K is algebraically closed. So you look at the equation f equal to 0, and you look for a solution. You would like to give a value to x1 inside the big K. So these are the set of all the roots of this polynomial inside the big K. But as we view this subvariety given by f inside the torus, we also ask the x1 to be different from 0. So these are actually the non-zero roots of f.
So is x1 a periodic variable because it's a torus or something like that?
No, this is called algebraic torus. It's not. I mean, it's not. This is because. I mean, if you view somehow, you can. So this algebraic, for example, if you are working with algebraic torus over C, it's C star over n. Okay. So if you look at the homotopy type of this, you can see that the C star over n, you can retract it to S1 over n, which is the torus, the real torus of dimension n. Because of this, and also some other analogies between C star n and the real torus, you call this algebraic torus. So this is an algebraic torus. There is no periodicity here. It's not like the case of real torus. I don't need actually any periodicity here. But in some situations, you decompose the C star n into you write it in polar coordinates, and then you get really a real torus, which corresponds to the phases, and then you have also the absolute values of the coordinates. Or
what is star n?
C star is the complex numbers, non-zero complex numbers power n.
Oh, I see.
Okay, so the C points of the Tn of the torus Tn are exactly C star power n. C star power n. That's this is the torus. Okay, so there's no periodicity. So if you're working, if you look at the solutions inside some field of this equation f, then the solutions are all the non-zero roots of. If you look at the solution here inside C, if A and B are like complex numbers, then you're looking at solutions of this equation, which are non-zero complex numbers. But so this big K is usually this big K has usually so I mean big K is like it can have a non-trivial valuation, and it can be equal to this small k, as I said. So in this case, A can be itself some function, some rational function which depends on a parameter t, and B also depends on a parameter t. So when you look at the solutions here, you look at it as a rational function or as a Puiseux series. Okay, so it's a little bit more complicated.
Complex variable?
Sorry?
Is x1 a complex variable?
X1 is a variable. It can take values which are not complex numbers, like it can have formal power series as values. If A and B are themselves formal power series, then the solutions exist only in formal power series. In formal power series, which have exponents also which are rational numbers. So that is the interesting case, because otherwise, if A and B were complex numbers, then the solutions are complex numbers and the valuations are zero. So the valuations are trivial if you look at non-zero roots. Okay, so in this case, the tropicalization of the set given by the zero set of this polynomial is exactly the evaluation of R and S are non-zero roots of F. Okay, so here I have to add the non-zero roots of F. So let's take a look at the case. You have the equation x1 plus x2 equals 0. So in this case, we are in the dimension 2. X is a subvariety of the algebraic torus of dimension 2. It is given by the equation x1 plus x2 equal to 0. And we are looking at the solutions inside K, big K. So big K is this field of Priso series, for example, which are non-zero, so non-zero solutions. But in this case, if x1 plus x2 is equal to 0, then it means that x1 is equal to minus x2. So then the valuation of x1 is the valuation of minus x2, which is the same. So the valuation of x1 will be equal to the valuation of x2. Okay, so this means that the tropicalization of x is basically all the points of the form AA, which lives in R squared. Okay, so in this case, the tropicalization of x is just the diagonal of in R2 given by the diagonal embedding of R, which is the set of all points AA inside R2. Okay, the more interesting case may be when you see that these equations which have some parameter t as coefficients, you look at a curve inside, again, you were in dimension 2, we look at the curve which is given by an equation of the form x1 plus t times x2 plus t squared equal to 0. Okay, so you would like to find the tropicalization of this. So what does this mean? It means that you have to put you give a value to x1, give a value to x2 such that this equation is satisfied. These values are taken inside the field of Priso series. Okay, so these are formal power series which have exponents which are rational numbers, and you should have this equation. And then what you do is that once you have a value for x1, x2, then you just remember the smallest exponent in this formal power series expansion of x1 and x2. And this gives you a point inside R squared. You look at all these points and you take the closure, the topological closure of this in R2. Okay, you see, it's I mean, if you want to calculate it like this, it's quite complicated because you have to solve you have to find all the solutions and then find the exponents and so on. So here, this is an observation which allows you to guess what should be what should be the shape of the tropicalization. So the idea is that you write if you have an equation of this form x1 plus tx2 plus x plus t2 equal to 0, then you write the equation in the form x1 is equal minus tx2 minus t squared. If you suppose that the valuation of x1 is a1, the valuation of x2 is a2, the valuation of t is 1. So you see that you get 3 values for this valuation, which are a1, 1 plus a2, and 2. Okay, and since you have an equation of this form, then you see that you should have the minimum between these 3 values should be achieved twice. So it means that the a1 should be either a1 is equal to 1 plus a2 is smaller than 2, or a1 is equal to 2 is smaller than 1 plus a2, or 1 plus a2 is equal to 2 is smaller than or equal to a1. And this gives you these 3 branches. Okay, so this is a guess, but this is actually the case that the tropicalization of this curve inside the algebraic torus of dimension 2 is this this shape, which is called the tropical line inside R2. Okay, so maybe I just make what this description more formal, and I state the fundamental theorem of tropical geometry. Okay, which is a way to provide an alternative characterization of tropicalization, which is much more handy and which allows you to basically see the appearance of polyhedral geometry out of algebraic equations. Okay, so what is the fundamental theorem? This is a way to make the discussion of the last example more precise. So let me start by a lemma, and this lemma is a basic lemma in valuation theory. So if you have a valuation which is defined over this big field K, this is the valuation V. You take two elements, A and B, and you suppose that the valuation of A is different from the valuation of B. And the lemma states that the valuation of A plus B is actually equal to the minimum of the valuation of A and the valuation of B. You remember the property concerning the valuations was that the valuation of the sum is at least the minimum of the valuations of the summons. But in the case the two valuations are different, then the valuation of the sum is actually equal to the minimum. Okay, so the proof is easy. Maybe I just skip the proof so that I can have time to go to the end of my my slide. But I will of course send you the slide so that you can see the proofs here. So the corollary of this lemma is that if you have more generally an equation of the form A1 plus A2 plus up to AM equal to 0, then you can prove that if you look at the valuations of the summons, then the minimum is achieved at least twice. It cannot happen that the minimum is achieved exactly once. And so in which situation we are going to apply this corollary and this lemma is exactly the situation where you are looking at the solutions of polynomial equations, and you are interested in tropicalizing the points which are in the solution, which are the solutions. Okay, so the situation is the following. You take F, which is an element in the ideal I of this subvariety of the algebraic torus. So it means that it is it's a Laurent polynomial in n variables. Okay, so I use the standard notation in basic in algebra. So you have variables x1, xn. Then F, you can write it as the sum Cj x power j, where x power j here means x1 power j1 times x2 power j2 up to xn power jn. And j is a vector here in z power n. So the exponents are, of course, allowed to take negative values because we are working with Laurent polynomials. Okay, so now if you have an equation, if you have a solution to this equation, which are given by giving values to the points, to the variables x1, xn, and f of that point x is equal to 0, then you look at the terms, you have a sum of the terms which is equal to 0. So you are in the situation to apply corollary here. If you apply this corollary, then you see that the valuation of the summons, the minimum value they take is achieved at least twice. Okay. So this gives you this this nice statement that if you have x, which is a k point of this subvariety x, you rewrite the tropicalization of the point as coordinates, having coordinates a1, an. So this is a point in R power n. Then you look at the valuation of the summons, the valuation of this product by the property of the definition of the valuation is that this valuation is V of the coefficient, the valuation of the coefficient, plus J1 exponent here, the valuation of X1, which is A1, so it gives you this A1, J1, J2 times the valuation of X2, which gives you A2, J2, and up to AN, J. So you see that this is an affine function in A1, AN, and the corollary here is that if you have a point x which has coordinates in this valued field k, when you take the tropicalization, you look at these affine functions and you evaluate this at the point trop x, at the point a1, an, then the minimum of these values is achieved at least twice. Okay, so this is basically a polyhedral description concerning a polynomial f. You look at the polynomial f, then you define this affine function by by looking at these expressions, and then you look at the set of all points in Rn where the minimum of these affine functions, when evaluated at those points, is achieved twice. This gives you a set, and then you intersect all these guys. It gives you the tropicalization of X, as you will see now here. So let me just define this for a polynomial. Yes. So there is a question.
Yeah. So I wanted to ask. So in the previous slide, the corollary also. So if the sum is 0, a1 up to n, then the minimum is achieved twice. And so if the corollary is true, when we are trying to look at the solutions of f, I mean,
this corollary is this corollary is the consequence of this. I mean, you can prove it by induction. Okay, so if you have a sum which is equal to 0, then the minimum of the valuation of the terms is achieved at least twice. I mean, it's not exactly twice, but at least twice.
Yeah.
So now you apply this corollary. You can apply it to this situation. Yeah, because if you have a polynomial of this form, if you take a point x where this polynomial is 0, it means that you are giving values to these variables, and this sum becomes equal to 0. So now you are in the situation of the previous corollary. You have a sum which is 0.
Yeah.
So then you can apply this to say that if you calculate the valuation of each summand, then you take the minimum of these values. The minimum is achieved at least twice.
Omid, her question is the converse true?
Ah.
Yeah.
I'm sorry. So what was, okay, I'm sorry.
Her question is the converse true? So if you have such a situation, V of A1 to V of AM, the minimum of that is attained at least twice, then can we conclude the converse?
That A1 plus AM is 0? No, of course, this is not true.
Yeah.
But so basically, I mean, maybe you would like to ask something more relaxed. So if you have a set of numbers such that the sum is 0, then you would like to find A1, AM such that the valuation of those is given by these numbers and the sum is 0. And this is true, yes.
Okay.
But yeah, I'm sorry, I didn't understand your question.
Thank you.
Yeah. Okay, so now you look at okay. So let me just then formalize what we said in the following way. You take a polynomial f, which is a polynomial, Laurent polynomial in n variables. You write it this way. Then you define the tropicalization of f by basically tropicalizing this formally. So you have a sum, you replace it by a tropical sum. Every time you have a product, you replace it by the tropical product. And the only thing is that, of course, this Cj doesn't exist in the tropical semifield. So you just take the valuation of this Cj. So you replace Cj by the valuation. So this is an expression. If you expand it, if you replace plus by mean and the tropical multiplication by sum, it gives you exactly these expressions, which are affine functions. So this trop of f is just the minimum of these affine functions. And you define the zero set of trop f as the set of all points a1 to an inside the Rn, such that the minimum of these terms evaluated at that point is achieved at least twice. So this is the zero set, tropical zero set somehow. And we saw that if you have the solutions of the equation f equal to 0, when you pass to the tropicalization, you get a 0 of trop of f. So then the fundamental theorem is this beautiful theorem, which tells you that when you have an algebraic variety inside the torus, tropicalization of x can be calculated very explicitly by looking at polynomial equations. So in the following way, the tropicalization of x is actually the zero set of tropicalization of the ideal. And tropicalization of the ideal of definition of x is the set of all tropicalizations of polynomials f inside the ideal. So what does this mean? It means that you take the intersection of the zero set of all the polynomials trop f, of tropical polynomials trop f. And what this precisely means, it means that you look at all the points A, which have coordinates a1, an, such that every time you have an equation f equal to the sum Cj x over j in I, then we look at the affine function you get out of the summand, which is just the valuation of Cj plus this linear function, which is the sum aj ai ji. This affine functions evaluated at this point a1 am take their minimum at least twice. So the minimum value you get is achieved at least twice. So this is somehow this answers, I think, the previous question. It tells you that basically, once you have these affine, these points which verify this property, then you can find actually an algebraic point, a point of xk, which has tropicalization given by this. I mean, somehow, because if you are looking the solution inside this big K, then the exponents, then these AIs are rational numbers. But up to enlarging your field, okay, allowing to have exponents which are real numbers, you can actually find an algebraic point, a point of x, which has a valuation given exactly to be A1, A2, and A. Okay, so now it's much easier to calculate the tropicalizations, to see what are the tropicalizations. For example, here you have this, you take an algebraic curve in dimension 2, in a torus of dimension 2, which is given by this equation. Then you see that the tropicalization of this polynomial is the expression minimum of W1, W2, and 0. So W1 is the valuation of x1, W2 is the valuation of x2, and 0 the valuation of 1. So you are just asking that the minimum between these three values is achieved at least twice. So this gives you these three lines, this line, this line, and this line. This is a tropicalization of a curve of degree 3. So you see it looks a little bit maybe mysterious, but here there's a way actually to calculate this. So this is going to be very succinct as exposed here, but in the notes I will share with you. You can find a more detailed description of this, how to find the tropicalization of a curve which is given by a polynomial equations in two variables, for example. Okay, so the idea is as yes.
Can you like? Hello. Yeah.
Hello. Yeah.
Can you go to the first example, like the previous page?
Yes.
I can't read what you have written. F equal to what is it really? In the first example, F is equal to the expression. I can't read what is written.
It's x1 plus x2 plus 1. I'm sorry, because I just added a lot of calculators. It's x1 plus it's x1 plus x2 plus 1.
Yeah, thanks. That's
okay, so then you tropicalize, you get just W1, W2. These are the valuation of x1, x2, and then the valuation of 1 is 0. So you ask the minimum of these three terms to be achieved at least twice. So for example, this half line is the place where W1 is equal to 0, and they are strictly smaller than 2. This is the point where all the three terms are equal. W1 is equal to W2 equal to 0. Okay.
So is the understanding that a curve of degree 3 or say degree n is given by a torus of genus 2 or n minus 1? Is that the understanding?
No. This is a curve of degree 3 means that you are having an equation which is of the form f equal to 0. F is a polynomial in two variables, x1 and x2, and the degree of this polynomial is equal to 3. This is a plane curve of degree 3.
Yeah, but how is it related to the torus?
So the torus here, this is the algebraic torus again. I don't look at, for now, I don't look at real torus. Algebraic torus means that you ask, if you look at the solution of this polynomial, you ask the coordinates of that solution to be non-zero. This is just this. The algebraic torus means that the coordinates are non-zero. So you look at the solution of f of x1, x2 equal to 0, asking that x1 and x2 should be non-zero. You don't allow x1 to be 0.
And that is the definition of the torus. That is the definition of the algebraic torus, you are saying.
The algebraic torus is the open subset of the affine space consisting of all the points which have all coordinates non-zero.
Okay.
Exactly. This is the definition of algebraic torus. Absolutely.
I have a question. In the degree 3 curve, the number of monomials that appear in the summation, is it equal to the number of lines that appear here, or is it something related to that?
So that is a very good question. So let me just maybe go. You will see exactly what are the. You mean the number of these unbounded lines?
Yes, yes.
Okay, so let me just go maybe then. So there is a way actually to define to see what is the tropicalization of a hypersurface. Maybe I just quickly describe this and then you will see. So there will be something related to subdivisions. Let me just, okay, so maybe I just take 5 minutes to explain this, and then if you have questions, I will be happy to answer, and then there will be more details in the notes I will send you. Okay, so what is the tropicalization of a hypersurface? This answers your question. Okay, so this is the case where you have just one equation. So you have, so X is given, is a subset of Tn, and it's the solution to a polynomial equation f equal to 0. It contains only one polynomial. This is a polynomial f, which is of the form the sum Cj xj. It's a Laurent polynomial. So to this polynomial, you can associate a basic polyhedral object, which is called the corresponding Newton polytope. Okay, so this is central. I think Newton studied this because of because it allows to control the solutions, the roots of polynomials. So this is obtained as follows: you take the convex hull of all the exponents j such that Cj is different from 0. For example, if you're working with polynomials in two variables, x1, x2, these are polynomials, so it means that the exponents are non-negative, and you assume that the degree is 3. So it means that the exponent of x1 plus the exponent of x2 is bounded by 3. So in this case, the Newton polytope is inside a triangle which has the two sides equal to 3. Yeah, because this is the set of, typically if all the coefficients of the monoms were non-zero, then you get it, the full triangle. This is the triangle which has the 3 vertices, 0, 0, 3, 0, and 0, 3. Okay, so this is the Newton polytope of a polynomial equation in two variables of degree 3, which have all the coordinates, all the coefficients non-zero, all the monoms, xi monomials, x1 power I, x2 power j, I plus j at most 3. In general, in higher dimension, you can define this object. Okay. So now, using this Newton polytope, there is a way to calculate the tropicalization. Okay. So the idea is that as follows. And it's a beautiful topic. I think this is just to maybe encourage you to look at it. This is the first time you see this. So the idea is as follows: you look at the coefficients Cj's. Okay, so this coefficient, you look at their valuations. So this gives you real numbers. So now inside this polytope, you have the corresponding exponent j. Yeah, because this is the convex hull, so it contains all the corresponding exponents. So now you look at this polytope and you lift j in one dimension up by seeing this lifting having height given by the valuation of Cj. So for example, here we are in dimension 1 in this example below. So there are 4 monomials in one variable. So the first monomial is x1 power m1. The second is x1 power m2, x1 power m3, x1 power m4. And you look at the valuation of the coefficient of x1 power m1, it gives you a number. You lift this point to this point here. Then you lift this point to this point here. You lift this point to this point here, and so on. And then what you do is that you take once you have done this lifting, then you also add all the points which are above this point in R2. So here, when you are working in n variables, it should be in Rn times R, in R times Rn. Okay, so you obtain these half lines, and then you take the convex hull of these half lines. It gives you this in this example. It gives you all this this chosen shape. Okay. So now what you do is that you look at the bounded faces of this, and there will be, in this example, there will be 2, and then you project this down to this Newton polytope, which was the convex hull of these points. This gives you a subdivision. In this example, it will be just 2 cells. Okay, and it happens that the shape of the tropicalization is given by this subdivision plus the remembering of the height. Okay. Okay, this is an example which allows you to answer your question. So if you're working, for example, in degree 3, then the corresponding Newton polytope is this triangle. Okay, this triangle has a vertex 0, 0, 3, 0, and 0, 3. And I'm assuming that all the exponents x1i, x2j for I plus j at most 3 have a non-zero coefficient, so that you can evaluate valuation of those guys. So when you do the picture of this lifting here, and you take the convex hull and you look at the bounded face, you then project them back to the Newton polytope. As one example, you can get this shape, where you have this subdivision, these triangles which are glued together in this form. Okay. Then the statement is that tropicalization of X in the case of hypersurfaces is given by this subdivision, in the sense that this is the dual to this subdivision. And the dual, you see the duality here is that for any triangle in the subdivision here, you have a point. Okay, these points are inside the tropicalization. And for any segment which is shared between 2 triangles, you have also a segment, the dual segment, which is inside the tropicalization of X. And the union of these gives you exactly the tropicalization of the K. So you see that the unbounded edges in the question which were asked correspond exactly to the segments which appear in the boundary of the Newton polytope of the degree 3 polynomial. Okay, so this gives you all the unbounded edges. That's why in this example, you have exactly 2 rays in these 3 directions. Okay, so the last example I have here concerns the case of hyperplane arrangements. I think this is central because the generalization of this and this example will provide building blocks for tropical varieties. But since I am out of time, maybe I just stop here and I will give this example next time.
Oh yeah, thank you so much. Thank you very much, Omid. Questions, comments? Yes.
Yeah, so I have a question. So is the understanding that you're calling it an algebraic torus because you're choosing the coordinates from a ring? Because essentially the ring is supposed to be kind of I mean, you could, for instance, the example of a ring would be the set of integers modulo some number. So we could have 1, 2, 3, 4, 8 up to 8, and then again back to 1.
Okay, so this is an algebraic torus because it is an algebraic group. Okay, so it's an algebraic variety which has a structure of a group, because I mean, you see, you can multiply if you have
that's the understanding. Yeah.
And I think maybe then you also see that if you're in the case of C, then C star power n, it is topologically it's a real torus.
Yeah.
So
topologically it's a torus, correct? That's what I'm saying.
So yes, but I mean, so if you are working and also for any if you look at the k points of this torus for any k, you get k star power n. So in a sense, this is given by allowing the coordinates to have an inverse and so on. So
yeah,
I mean, so this is the terminology given by to this algebraic variety. It is called an algebraic torus. But I mean, maybe we can call it T. So this is somehow So as I said, I mean, so this terminology comes from the developed geometry in which these algebraic groups play a central role, which is called toric geometry. And toric geometry is a generalization of the projective geometry, and these examples are affine space, toric, these algebraic torus are examples of, and everything. Maybe some of the things that will show up later or examples of the objects in toric geometry. So basically, we are interested in sub-varieties which live inside some toric variety. So the varieties themselves are not toric, but they are given coordinates by some toric variety. So yeah, and this tells us a lot, because we can use those coordinates to tropicalize and pass from algebraic setting to the polyhedral setting.
And what exactly is the point of tropicalization? You get other manifolds or something like that. Is that the point, or is there anything?
As you see, it's not always a manifold, yeah, because it is, as you see, it is completely. There are a lot of singularities here.
Yeah.
But
So,
the aim of the lectures here is that actually in these situations you get something which is somehow smooth.
Smooth.
Okay? So it's, yeah. So I mean, this is you see that there are some singularities here, but yeah, as I will explain later, you can define a notion of a smoothness so that you can view these things as being smooth. And then you can ask what are the tropicalizations which are good. So what is the purpose of tropicalization? The tropicalization is a procedure to simplify the algebraic variety, because there are a lot of informations, maybe you don't need them. So the tropicalization allows you to simplify. And in some sense, in some cases, it allows you also to gather the algebraic information. For example, if you're interested in defining compactifications, or in adding these missing fibers, if you have one parameter families which are defined over some, like punctured disk, for example, then tropicalization can be used to reorganize the data, the structure of this family, so that you can find a way to add, to include a fiber, which is as nice as possible. Tropicalization is a way to simplify and then reorganize to get something algebraic back. So at this point, I'm just trying to tell you, this lecture was to explain you how you can simplify algebraic varieties. And the simplification was really basic. It looks like brutal because from the solutions of polynomial equations, you just remember the valuation of the coordinates. So it looks like something very brutal. But we will see that this remembers, in many situations, this remembers a lot of information and allows you to say interesting things, both in the context of where you study geometry of algebraic varieties, complex varieties, for example, or in the situation where you are interested in purely combinatorial questions. Okay, so that's I think the message of the lectures, and there will be some talks. But I hope that this answers your question.
Yeah, so for instance, if a field is defined, a field in the sense of physics is defined in terms of a manifold or an algebraic variety, then that would correspond to a fiber, right? I mean, for instance, if a fiber of infinite dimensions, if a field is defined on a vector field, for instance, if it's defined on the manifold or the algebraic variety, that would correspond to a fiber, the sort of fiber you're talking about, right?
No. I mean, so no. So what I was talking was like, for example, you look at this. Maybe I just come back to these examples of. So, for example, you look at this example. These are polynomial equations which depend on one parameter t. Okay, this t is a parameter. You can view these. So if each time you fix t, you get some equation which doesn't depend on t because you have given a value to t. For example, you put t equal to 10, you get x1 plus 10, x2 plus 100 equal to 0. Now you look at the solutions of this, you get a curve. You get a complex curve if you look at the solutions inside the C. Now you give another value to t. You put t equal 100, you get another solution. You put t equal to I, you get another solution. So this defines a family of solutions which are parameterized by t. So if you choose t generically, I mean, you just give a random value to t, then you get something which is smooth. But if you put a t, like very badly, choose it I mean, yeah, so there are some values for t, so that you get something which is badly singular. Okay. So the fiber, the replacement I'm talking will replace that singular fiber, which is very bad, maybe badly singular, by something which is as nice as possible.
Okay.
Yeah. And the tropical geometry allows you to do this. That's what I'm saying. The tropical geometry allows you to do this procedure of basically it allows you to remember the essential information to be able to replace the fiber by something nice.
So essentially you're smoothing out the singularities by this method.
Just a second, please. Maybe we can there are some other questions here.
Yes, please.
Yeah, I just had a basic question. So I wanted to know how is Tn an open set in the affine space?
Because it is given. So if you look at the coordinate xi equal to 0, it gives you a closed set. Yeah, this is given by one equation. It's a Zariski closed. For example, you take you look at the first variable x1. You put x1 different from 0. This is the complement to the equation x1 equal to 0 in the affine space. But x1 equal to 0 is an affine space of dimension 1 less, which is closed, because this is given by equation x1 equal to 0. So the complement is open.
Okay, thank you.
So if you, yeah, I mean, if you take the union of xi is equal to 0, you take the complement, it's exactly the torus. That's why it is an affine. That's open set.
Thank you.
Hello.
Hello, yes.
Yeah, so I wanted to ask, can you please explain again this dual subdivision? The last picture you drew.
Yes, so, okay. Okay, so what I was saying is that...
So if I understand correctly, your sub-triangles are basically the lattice point of the exponents, right?
Exactly. So these points are the lattice points of the triangle. And
now how do you draw these unbounded edges?
Not always they show up, okay? Because it depends if there is an exponent, if that exponent is present in your polynomial or not. And even if it is present, it depends on the way, on the valuation of the coefficient. Sometimes they show up. And this is an example where every point in the Newton polytope shows up. Okay, and you get this subdivision. This subdivision, you get it by doing this procedure, by lifting the integer points to some point in one dimension higher by adding this height function. Yeah, this is one dimension up. You increase the dimension by 1. Then you lift the points, the integer points in that dimension. So here, for example, this point has been lifted to here. You lift all the exponents, all the points which correspond to exponent in the Newton polytope, and then you take the half lines starting from that liftings, which go up. Then you take the convex hull of this point, these half lines. It gives you a polyhedral set. So as you see, a lot of faces of these polyhedral sets are unbounded, but there are some which are bounded. Then those bounded sets, bounded faces, when you project them back to Rn, gives you a subdivision of the Newton polytope. In this case, you obtain this subdivision. Okay, so it means that there is something, there is this convex hull of this half line, which is above in dimension 3, which is above this subdivision, and you have projected down the bounded faces. Okay, so now how you get the dual, these dual red segments. Okay, so the idea is that every time you see a polygon here in this subdivision, this is the triangle. it corresponds to 3 terms in the polynomial you started with. Okay.
So that trivalent thing is just a line, right?
The which one?
In each triangle, the 3 rays
corresponds
is basically
to a
line.
Yeah. Exactly. So exactly. So that is a good point. Actually, there is a way to make this precise. That locally, you see just lines. Okay. You see that locally around each point, you just see lines. This is also a line. This is a line. Locally here, so you see just a tropical line. But you have, I mean, you have to. But what you see is that. But you have to say what is this point. To say that what is this point, you have to find this point corresponds to a solution, to a zero, to a tropical zero of the tropicalization of the polynomial, and it is the minimum of 3 terms. Okay, so if you have 3 affine functions in 2 variables and you ask them to be equal, you get 2 equations. Yeah, because you have 3 affine functions in 2 variables, you ask them to be equal, and they should be minimum among all the affine functions you see in the tropicalization of the polynomial. You get 2 equations in 2 variables, and it gives you a unique point, and this is that point. Okay. You add all these points inside here, and then you have the segments that will show up, and these segments are the points where these 2, the corresponding 2 monomials, are equal. So of course, when you have 2 affine functions, you have put them equal, you get the set of solutions is a line. Yeah, is an affine line. But then you have all the inequalities which tell you that this should be the minimum among all the terms, and this gives you a half line. These are the half lines.
Yes.
Or if you are internal, you get a segment because you are bounded from both sides. You get a segment. Okay, so what is the question?
So in the interior, you don't have this unbounded edges?
No, in the interior you don't have, because you are bounded. You start from here, then you know that you are unbounded in one direction, which goes out of the triangle.
Oh,
you start from this side, you know that you are unbounded from the other. You can be only unbounded from the first point. You see that you can be unbounded only in the direction which goes outside. Yeah. You start from here, you get that you can be unbounded only in the direction which goes outside. Then you should be unbounded from both directions. That is why it is a segment.
Thanks.
Okay.
Thanks.
Yeah.
Any other questions? Offline audience, online audience? Okay, thank you very much, Omid, for your patience. Yeah, for the very accessible, nice lecture. So we'll continue tomorrow. Again, the same time. So please watch out for the next lecture. Very interesting coming up. Yeah. Thank you very much, Omid.
Yeah, thank you very much. Yeah. See you tomorrow then.